Okay, we can start with a new model. New model. Pay attention, of course, on the unity. Last time we talked about abacus. In abacus, you don't have to define the unity because everything is depend on your choose. In SAP, you have to pay attention on the unity. So we can start with a general model, grid-only model. And okay, I can create, then I will modify, so I can create something like this. Okay, first of all, we have to create the grid. Now I'm going to realize a cantilever beam, so the grid will be really simple. So right click on the screen, you will have something like this. If we modify the global grid system, we can define a plane in the X and Z axis. I don't want to consider Y axis because I'm going to design my beam, my cantilever beam in X zeta. So maybe I can create like 2 points or 3 points in X. I have to check the length of the problem. Okay, 2000, so I can put 1000 and 2000. And I can create something in zeta, but it's not important because I'm going to design my beam in X direction. So I can create something like 100 in order to have a point, a grid also in zeta. Okay, this is the grid. So the problem that I wanted to resolve is a cantilever beam. So free end and fixed end. The section is WT EPA 330. And the length is 2 meters. I wanted to study the buckling. So first of all, we can define the cross-section and the material. Define. In SAP, it's better to start with the material because then in the cross-section we have to choose the material. So firstly, we have to create the material. I don't want to use these materials, so I want to create a new one. Add new material. It's not really important for this analysis because buckling is a linear analysis. So it's not really important which type of material you are going to choose for the buckling. But okay, we can choose Italy. You can see that we have steel, concrete, and you can see also we have the codes, NTC and another, at the grade of the material. It's not important now. Okay, we can choose steel, Italy, and S355. If you look at the material properties, you will have the weight, you will have the elastic modulus, that is the parameter that we are interested in, because as you know, the buckling formula is this one. So elastic modulus is inside our formula, our equation. Poisson ratio is important also because the shear modulus depends on the Young modulus and on the Poisson ratio. So we are going to choose the value, classical value for steel, that are these two. And we are not interested now in the yield stress and ultimate stress and so on, because as I told you, buckling is a linear analysis. We can delete the other material because I don't need. Okay, now I'm going to define the cross section. Frame sections, because I want to create a beam element. You have other types of cross section, like this one for the shell elements, or this one are for the links, for the spring, for the semi-rigid joints. Frame sections. SAP is really easy because you have a list of with a lot of cross section inside of SAP, so I can choose directly this kind of cross section. I can import a new cross section, double T cross section. I use Euro. There are some different lists. This is the classical one for European profile. So you can see there is a list with a lot of profiles. And I'm going to look for the one that I'm interested in. This one. Okay, the first thing to do is to assign the material. Then we have to check properties with a manual. You can find on internet the properties, or you can calculate by hand properties, and then you can check properties if they are right or not, because they can be a little different, because in some software they can consider in a different way this radius. Maybe they can consider this perfectly sharp, or you can have some differences, for example, in the C section. When they discretize the medium line, they can use different algorithms, and so you can have quite different from the theoretical values. So these are the values of SAP. You can see cross-sectional area, second moment of area, torsional constant, and of course plastic modulus and the radius of gyration. In SAP, shear eccentricity is not working, so don't pay attention on this value, because the 6 degrees of freedom beam have not the capacity to account in the formulation the shear center position. So it's not important. I don't know why they report this value. We can check with the theoretical properties. You can see the cross-sectional area is, I can do a zoom. Where is that? But I don't find it. Okay, you can see the cross-sectional area is the same, and also the other properties. Okay, we can observe that I reported also the warping inertia. Warping inertia is important for calculating flexural torsional and torsional buckling. But in SAP, like in the other programs with beam having 6 degrees of freedom on each node, they are not able to use this property in the calculation of flexural and torsional buckling and torsional buckling. So with these 6 beam elements, you are not able to calculate a flexural torsional buckling. You will obtain a value that is wrong, is different from the value that you expect from the theory. Okay, now we have checked the cross-section properties. You can see here that you have the set modifier. So if there is something wrong, you can simply change it by multiply the properties by a value. So if your property is 1.1 less, you can put here 1.1 and change the property. I'm going to put a higher shear area because I don't want to consider shear deformation in the buckling. We can put also 0 in the mass and weight because I don't want to consider self-weight. But in SAP there are 2 ways to do this. Okay, now I'm going to put 0 here. Okay, we can create now the beam element. Here you have a draw element, frame or element, or here, or on the left. Pay attention on this menu. You have straight frame or curved frame. You can choose the section directly here. And you can choose if they are pinned, like if you want to realize trussed beam, you can put directly here that all the joints are pinned, so you don't have to release this day after. So now I'm going to put continuous because my beam is continuous, and I'm going to draw it. It's important to create a grid before drawing because if you don't have grid, you cannot choose the point, so you cannot draw your beam. I'm going to create a unique beam element in order to show the influence of the mesh. So now is only one element with a length of 2 meters. Now the very important task is pay attention in the direction on which you design, because it changes your local axis. Now I'm designed from left to right. If you look at the local axis, we have the local axis 1 in this direction. If I design from right to left, you can see that the local axis is in the other direction. This is important because when you have a very complicated frame, maybe you cannot understand the results because of some axes are rotated and you are not able to understand if the bending moment is positive, negative, in X direction, in Y direction. Local axes are important also for the cross-section orientation, as I told you last time. If we want to see the 3D, in SAP we have also the opportunity to see the 3D. Now I designed this type of beam. If I want to design beam in the other direction, I can use local axis modifier and rotate the local axis. Is in a sine frame local axis. we can put here 90, for example, 90 degree. You can see that the beam is rotated. Okay, now we can fix one end. It's really simple in SAP because you have directly assigned external restraint in joints. So there is this menu with joints. You have a lot of things. I'm going to assign restraints that are external boundary condition. I want to fix everything. So you have this kind of design that is the classical one for the fixed joint. I'm going to select one end and apply. Really simple. So you have this kind of symbol. The symbol depends on your, of course, your boundary condition. If I choose only translation and no rotation, this symbol will change. The last thing to do is to apply the load. First of all, we have to create the load patterns. So define load patterns. Pay attention now because in SAP you have this kind of task that is the self-weight multiplier. Okay, now we have put 0 on the weight, so now is not important. But if you not put 0, here, if you don't want to consider self-weight, you have to put 0 here. So this is really important because if you want to consider self-weight only on dead load, you have to put 1 only on dead load. If you want to create like a wind load, pay attention to put 0. Because instead you will consider self-weight 2 times. Now I'm going to create a live load. Automatically you will have 0. I'm going to create a load called like axial load. Okay? To assign a load is really easy also. Again, assign, you can see here that we have joint loads and we can assign forces and displacement. So it's really simple. Now we are interested in forces. Once again, paying attention if you are looking on global or local direction. This, of course, is really simple in one beam, but if you have something that is not simple, pay attention. And we are going to select our load pattern that is axial. Okay, now 2 words about the force. Buckling is a linear analysis. So, if the buckling multiplier is the buckling of our beam is like 50 kilonewton, for example, if I put here 1, I will obtain from the buckling analysis that the multiplier is 50. So this is a linear analysis. If I put here 10, I will obtain 5. Simple. Because the equation is axial load, the critical buckling is axial load multiplied by the multiplier, the elastic multiplier. Okay? So I'm going to put, for example, 1 kilonewton. So 1000 Newton. Okay, now everything is ready. We can calculate the buckling by hand by using the classical equation. Pay attention on these terms because we don't have only flexural buckling. We have also torsional buckling and flexural torsional buckling. Of course, in a double symmetrical cross-section, there is no problem of flexural torsional buckling. But in some asymmetrical cross-section, you can have problem of torsional buckling, like in this kind of section. When you have a C section, you don't have the coincidence between centroid and the shear center. The behavior of the cross-section depends everything on the shear center. So also the buckling will be a mix between the torsional and the flexural. Buckling will be something like this, flexural and torsional. So you will have problem with flexural torsional buckling on this cross section. And with SAP, you will not able to calculate this kind of buckling. You need 7 degree of freedom software or something like more sophisticated, like shell analysis or straight line, something like this, or abacus with a shell, complete shell model. I calculated the flexural and torsional buckling. Of course, pay attention on the buckling length. This is not the length when you use this formula. This is not the length of our beam, but is the buckling length, okay? When you have a cantilever beam, there is a factor of 2. Because this is our beam, this is our buckling length. So L with 0 is 2 times L. If you have a double pinned beam, you will have 1. L0 is equal to L. And so on. If you have something like this, it changes again, it's 0.7. For this case, L0 is 4 meters. Okay, you can see that the minimum buckling is, of course, the buckling in the weak direction, in the zeta direction, because we have the same restraint in this direction and in the other direction. So, of course, the buckling will be the one, the minimum one will be the one in the other direction. But you can have also different restraint condition. You can have something like a rack frame, something like this. So this beam will have this buckling length in this direction, and in the other direction we will have this buckling length. So when you use this formula, you will have the extra buckling around y direction, that is depending on the second moment of area and the buckling length in this direction, and you have the other buckling depends on the other second moment of area and on the other length. Now it's more simple because we have the same restraint condition, so we have the same buckling length in this direction and in the other direction. So we can perform the analysis. Okay, the minimum buckling is 1021. I expected this value. And as I told you last time, since this is a validation of a simple case, I expect exactly this value, not something similar. So we can define, now the most important thing is to define the load cases. Here there are some cases automatically created by SAP. We can delete it. We have to add the new load case. And also this task in SAP is really simple because you have buckling. We can use a name like buckling. This scale factor is a scale factor on which you can use it to multiply your load by a factor. So if you put 1, your load will be multiplied by 1. If you put 0, your load will be multiplied by 0 and will not consider. This is not important because you can select a very lot of number of buckling modes. If you have a very big frame, you can have like 200 or 500 buckling modes. But we are interested in the first positive one, so 6 values can be okay. We can run analysis, so you can press F5 or you can use this play button. That is the classical play button. And we can run the analysis. Of course, SAP, you need to save the file before running the analysis. Okay, now we have this kind of value. You can see that is the buckling in the weak direction, so in this direction, as I expected, and the value is similar. It's not exactly. Maybe we can refine the results by using more elements. Okay, now it's perfect. It's exactly 1021. You can see this kind of buckling. this is our buckling, the buckling of our beam. But you have also information about the other modes of buckling, the higher modes. So I expected a mode that is torsional, but I told you that SAP are not able to calculate it. So I'm not expected to see with SAP this 2398. But I expect to see this one, the flexural in the other direction. 15242. So you can go with this arrow, you can select the second mode. The second mode is a higher mode of the first mode. So you can find with this equation, this kind of mode is a sinusoidal mode. But you can see that we didn't find the torsional one because it's passed from the previous one to this one that is 9187. Okay, this mode is the flexural one in the other direction. And I expect that the behavior is around the y-axis and is this kind of behavior. Is a flexural behavior, okay. If I look to the other modes, I will find sinusoidal modes that are not interesting for our case. Okay, so what we have discovered, using SAP, buckling is working well because we obtain exactly this number, but you are not able to resolve this problem. So you can try to use these equations at home and try to calculate flexural, torsional, and flexural torsional buckling of this cis cross section. You have the property here. Then you can try to insert in SAP this cross section, perform a buckling, and you will obtain the flexural value, always, but will not the minimum value for this case. Everything clear with buckling? Okay. We can look at second order analysis. Professor Berluzzi told me that you know about this equivalent lateral force method. That is an approximate method to perform second order analysis. The situation is this one. And we have two different cross-sections. The second one is more slender than the first one. What happens when a frame or a cross-section is slender? The buckling will be low. And this beam will be sensitive to the second order effects. So, if you have this frame and another frame if the second one is more stiffer than the first one, for example, you will have a buckling here that is like 15 and here like 5. What happens for the design point of view? From the design point of view, here you have to perform the first order analysis. So internal actions will be obtained from a first order analysis. And also if you perform second order analysis, results will be similar. In the second case, internal action and displacement arising from the second order analysis will be greater than the one obtained from the first order analysis, because this frame is more flexible. And if you look at Eurocode, if you have this situation, you have to use always a second order analysis. So you have to design your frame by considering displacement and internal actions arising from a second order analysis, or at least first order analysis amplified. This is why buckling is so important, because you can understand immediately if your frame is a flexible frame or a rigid frame. We're working with the Rax frames, the one that I showed you before. In this kind of frame, we can have buckling of 1.5 or 2. So you can imagine the flexibility of this frame. Okay, return to our exercise. You can see, as I told you, the first beam is more stiffer than the second one, as you can see also from the second moment of area. And if we calculate the buckling mode, the buckling value, you have in the first beam the value of 3, and in the second one a value of 1.1. So this beam is near to the collapse, because when the buckling is 1, we have problem. This beam stay not so good, but is not so near to the collapse. The flow chart of the procedure is an iterative procedure, but I know that you know, so I don't want to spend time on this. I wanted to model the beam on the SAP. So I can model the first one, then you can model the second one at home. Okay. I'm going to erase everything, and I'm going to check the length is 6 meters. So I'm going to modify the grid data in order to have the points on which design my beams. You have to import, of course, a new cross-section. Again, I can import a new cross-section, Of course, you can also design a cross-section in SAP. If you want to add a new cross-section that is not imported, you have two options. Or you can choose a cross-section and changing the dimension, or you can design completely from zero a cross-section. Here you can design a cross-section and import. SAP automatically will calculate the properties. Another option is to define the properties without design anything, with a general cross-section. You can see that you can put the properties by hand. Cross-sectional area, inertia, and so on. So you have a lot of options. But for our problem, the cross-section, of course, are simple, so I can import it. I'm going to choose the first one, so 280. Again, I'm going to put, I don't want to consider shear deformation. And I wanted to put 0 in the mass and the weight. Now we have to design our beam. Pay attention now when you design to choose the right cross-section. Continuous, of course. From left to right. And I'm going to divide this beam in more elements to have a more refined results. To divide, you have edit. With edit, you can do a lot of things like moving nodes, replicate some parts of your structures. So you can have, for example, a plane frame. You want to have a lot of frames that are equal to each other. You can replicate. I can divide our lines and choosing 10, for example. So we have 20 elements. Since our analysis is only in the plane of the blackboard, I don't want to consider effect out of plane. So there is an option in SAP. This is a very, very useful option. You cannot find in a lot of software. We can avoid degree of freedom, for example, out of x zeta plane. I wanted to say consider only what happens in x zeta plane and do not consider degree of freedom in other planes. Okay, now is simple because we have to define again the fixed end. And we have to define the load condition. I'm going to create 3 different loads, or I can put everything. I'm going to create 3 different loads: axial load, lateral forces, and moment. And I'm going to create the load condition. Again, joint loads forces. Okay, now I created 3 different load patterns, so I have to assign 3 different loads. If you use only one load pattern, you can define everything in this menu. But I have to choose axial and define the axial value. I have to choose lateral force and put lateral force. Of course, it's not in X, but is in zeta. Okay. And I'm going to put also the bending moment that is in around Y direction. Pay attention on the unity. I think you can write also here multiplication, like 40 multiplied by 10. Yeah, you can write also 40, like this one. Yeah. Or you can change on the bottom of your screen the unity every time you want. You have a lot of unity. I don't remember if I have assigned the load. No, I think I didn't assign it. So joint load, moment, okay, apply. Okay, now we have also the bending moment. Okay, is right. Okay, we can start with the first order analysis. I am going to use also buckling. So buckling, first order is really simple because it's static analysis, linear analysis. I'm going to select all the loads: axial load, lateral force, bending moment. Okay. For the second order analysis, you have to select again static analysis and nonlinear static analysis. But pay attention, it's not sufficient to select only nonlinear. You have also to select p-delta effects. This is the problem that I told you before. In some software, you can perform a large displacement analysis. In SAP, you cannot do this. So don't use large displacement. Or I don't know if the new version is okay, but with the old version, there were some problem with the large displacement analysis. So use only p-delta effects. Again, axial, lateral force, and bending moment. If you look at this menu, there is a display deformed shape. You can press F8 or you can use this menu. So here, sorry, F8 is for the internal action, F6 is for the displacement. You can see here what kind of analysis you want to see and the mode numbers if you have the buckling analysis, or the step if you have nonlinear analysis, step-by-step analysis. So first mode, If you want to calculate the buckling of this beam, of course, the first mode will be the mode out of plane, not this one. This one is in plane mode. This is why the first mode is this one, because I fixed everything out of plane. So the only behavior of my beam is in the plane x zeta, in the blackboard plane. 3.07 is exactly the value that I expected from the theory. So again, buckling is okay. What happens to the second order effects? We can return to x zeta plane. Okay, first of all, we can check the displacement of the first order displacement. From the theory, it's really simple to calculate the first order displacement because it's a superposition effect. So we have this plus this. This is and this is because it's linear. From the theory, we have 50.2 millimeters. From SAP, you can go on the node that you want to see. You will have displacement directly on the screen. I'm interested on the top displacement. Okay, 50.16, so is exactly the one. You can do right click on the node. You will have this menu with the displacement. You can use tables, selecting the node, for example. If you push Ctrl plus T, you will have this kind of tables. Here you can select your output if you are interested in the displacement, in the internal action, in the reaction, in the modal vibration problem, and so on. We can look also in the bending moment. Again, the bending moment will be the sum of these two moments. You will have this moment that will be 10 plus multiplied by 6, that is the length. So 60 kilonewton meter plus this one that is constant, that is 40. So the first order bending moment will be 100. You can use this type of show for stresses to show frame stresses or joints output. You can show frame stresses from the first order analysis, and you can choose the moment in which you are interested. This is the diagram of your bending moment. It's a sum of these two types of moments. So in the top we have 40 and in the bottom we have 100. If you put a right click with the mouse on the beam, you will have the behavior of the diagram of the internal actions along your beam. Okay, you can see that the results is exactly 100. We can choose kilonewton meter. You can see that is 100. Okay, now everything is perfect. Now we can look at the second order displacement, because I performed also the second order analysis. So here I'm going to select second order. From the theory is an approximate procedure, so is not really exact, but we can check if is something similar. Is 68.1. From SAP we have 66.6. So first order are 50.2, second order are 66.6. That means for this beam you will have an increment of 1.32 times on the displacement. We can do a second order approximate analysis by using a very simple equation, that is this one. Delta on second order are equal to delta first order multiplied by this equation. We can check if this equation is working or not. The critical load was 3.07, and the first order displacement is 50/0.2. This equation gives me 74. So of course it's approximate equation and the value is higher, but it's not a problem. If you don't want to perform analysis, you can use this. We can look at the bending moments. First order was 100 kilonewton meter. And second order is 132. So again, 1.3 greater than the first order one. So here we have 100, here 132. I wanted to show you one interesting thing. I told you that the geometrical mass matrix depends only on the axial value on your beam. And the second order is directly dependent on the axial value. If I put 0 in the axial value, so if I don't have axial load, and I'm going to perform a second order analysis, you can see that is a second order. You can see that there is no difference between first order and second order. Exactly the same. because again, the geometrical stiffness matrix in SAP depends only on the actual value. So if you don't have actual value, you don't have geometrical stiffness matrix. As a confirmation of this problem, I can do another. We can perform a buckling analysis by using only lateral force and bending moment without considering axial load. So I'm going to do not run these two cases, only buckling. So no results. You can see that I don't have results because I don't have axial load, so I don't have the geometrical stiffness matrix. The last thing is if I put for this beam axial load, moment load, lateral force, and I run again buckling, I will obtain again 3.07. Exactly the same that I have obtained with only the axial force. This is not so usual because if you use another software, the stiffness geometrical matrix depends also on the bending moment and not only on the axial force. So you will choose different buckling values. In SAP, these situations are exactly the same. So pay attention also in this option when you perform a second order analysis or a buckling analysis. Because like in another software, they ask you want to consider only axial forces or you want to consider a bending moment and so on. I think you can check, so if you want to try to use SAP at home or now, you can try to design this frame. It's a really simple frame because you have to design only 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 8 columns and 6 beams. And you have to put distributed loads and performing a buckling analysis. If you want to try to do this now, I can help you with this frame. Do you have SAP here? Okay. I can